Sorry, Ryan. Okay, so anyway, that's just kind of a look at all that. All right, so this is what I had up here the other day, and you may have written this down, and so I'll just throw this up here again. So the quiz tomorrow is going to be a lot of chart, global max min kind of stuff, probably with some trig in there, maybe some of the polynomial stuff. Those are the two that have, a lot of ups and downs and give you nice local max min inflection point kind of scenarios. Okay, so it's a good chance for us to work on those. The differential equation stuff, we did some verify. We'll get into that here a little bit today. Of course, your bank interest, if you see a bank interest kind of problem, something with money, that kind of thing, exponential growth, you're dealing with that function here. And that's where that antiderivative can come in. And then there's some problems where it's just, here's f, find f prime. Find f double prime or whatever, where you just do that. But inside of a lot of these problems, you're going to be doing that as well. Okay? So that's it. If you can do those things, should be good to go. Okay? Sounds easy, but we'll see. So then, of course, we had our derivative rules that we wrote down. These, right now, I don't think these are a big deal to write down. Maybe you have them written down, maybe not. But this just says we can add up. We do the individual derivatives here. If you got a number set out in front, it just hangs out there. If you got a number on the inside, you got to kick it out. Right? Talk about that. Of course, we got our power rule. E to the x is its own derivative. If you got another one, like 2 to the x, then you have to kick out that 2, or that ln2. So 2 to the x would be 2 to the x ln2. 3 to the x would be 3 to the x ln3. Okay? And then ln x, so Harish asked about this, so either maybe you want to jot these down again, but ln x, the derivative, that's 1 over x. And then if you got another base, 10, or some other base, then it's 1 over x, and then 1 over ln. Okay, so log base 2 would be 1 over x, and then 1 times 1 over ln. Okay? All right, and those are all written out in those sections as well. And then don't worry about this bottom one. And of course, the derivative of sine is cosine, and the derivative of cosine is negative sine. And secant, derivative of tangent, secant squared, that's not going to show up. So derivative of sine is cosine, derivative of cosine is cosine. Okay? All right, so then, again, chart stuff, which is local max min, inflection points, increasing, decreasing, concave up, concave down, and then, of course, global max min is when we do our list of candidates, which is where the derivative 0 and the endpoints. Derivative 0 or the endpoints. And we plug those back into the original function, see which one's biggest, see which y value is biggest, which y value is the biggest. Okay? And then the differential equation stuff, we said it's an equation that contains derivatives, and the solution to a differential equation is the original function. Then we added in this idea of IVP. IVP is an initial value problem. Has an initial condition. Number 10 or 11 is one of those. We'll talk about it here in a second. Okay? And then we said the 3 different types of differential equations. That type we can just easily solve by doing an antiderivative. Remember, solve means get the original function. So we got y prime. We want to go to y, the original function. Okay? We can't solve, but we'll just memorize it. And that's our bank one, or exponential growth one. And then there's those ones we don't solve, like number 48. We don't know how to solve number 48. It's not a bank interest, it has square root in it. But we can verify a solution with the t-chart. Okay? So those are the different types of differential equations we had. Okay, and there you go. So there's a quick rundown of all that stuff. Now let's do some problems and let's see how that connects all that stuff.
Do you see that you'll give us like another one, but
yeah, that Newton's law of cooling we talked about later on, not for this quiz, later. Okay, all right. So I've got down here. This is on section 2.5, I believe. I've got 24 down as just. Was this the one? Were we talking about this one? Was this the one we were mentioning? So I thought I would just look at this now. Again, I just wrote it out. I don't remember if this is how they gave it to you, the order they gave it to you, whatever. But this is the part that sometimes people get confused by. Where does the t go if I'm doing a t-chart? Because right now this problem is verify. Verify the solution. Where does the t go? The first one or the second one? Second one, right? Second one. It goes in the differential equation. It goes right here, right? This is the solution. Remember, the original equation is the solution. So the y equals is the solution. So the t goes here. Okay, so y double prime. So I'm going to need y prime. So that's 2x plus x to the negative 2. And y double prime is 2 minus 2x to the negative 3. So there's y double prime. So that's just using our derivative rule. Okay? So that goes there. So 2 minus 2x to the negative 3 minus, now in place of the y, I'm going to put that. So that's going to be x squared minus x to the negative 1 all over x squared. And then this side, there's nothing to do. So on this side, what I would recommend, so this is some algebra. Some problems have a little more algebra work to do than others. This one definitely has some algebra. So if I was doing this, I would probably distribute that negative 2 through there. I would turn that into a plus. And then I would make that negative 2x squared plus 2x to the negative 1 all over x squared. Okay, I would turn this into plus and make that a negative 2, just like that. Okay? All right. Now, so I distribute that. Now, when I see this, what I talked to you about this, most of the time this year it's best to do what here? Separate that out. Let's split that out. So this is going to be 2 minus 2x to the negative 3. Now, I'm going to put this on top of this. So that's going to be 2x squared over x squared. What's going to happen? So that's going to be minus 2. And then I'm going to have 2x to the negative 1 over x squared. Now I can subtract those powers. What's negative 1 take away 2? Negative 3. So that's going to be plus 2x to the negative 3. Oh, that's nice. 2 minus 2. That cancels that. See. Check. Okay? So, you got to do a little algebra, but things cancel out. Okay? You got to show that to get the full credit there. All right, so 23, 24, we're kind of that. This is definitely something we would have no idea how to get the original y, but we can verify it's a solution. Okay, let's talk about 48. Okay, so 48 is a big old problem. It's a good problem. Torricelli's law. You got a cylindrical tank with a valve at the bottom. Well, just think of one of those big old orange water coolers, Gatorade coolers, right? That's what we're talking about, right? Now, the first question, part A, does it come out faster when it's full or half full? I mean, just common sense. When it's what? It's full, right? You've all sat there and tipped one of those over trying to get something out, right? Because it comes out so slow, right? When it's full, right? It has to do with pressure, stuff like that. But that's what this is saying. From a mathematical perspective, if I ask you to explain that, you would say, because y prime is going to be bigger when y is bigger. And y is the depth of the liquid. So when the y in this, that's what proportional to means. So the rate that the liquid drops, and that's what now, to be honest, we talked the other day about turning one of these from words into an equation. I would submit to you that you should have been able to write this differential equation. Let's read those words. It says, when the valve at the bottom of a cylindrical tank is open, the depth of the liquid in the tank, and I would probably tell you what to call that, maybe, right? I'd tell you to let y be the depth of the liquid. If y is the depth of the liquid, when the tank is open, the depth of the liquid drops at a rate, so right there, y prime would be your rate, is equals proportional to, so we'd stick in a k when it says proportional to, the square root of the depth of the liquid. The square root of y, right? That sentence right there, we should have been able to take that and write that. Now, why is there a negative there? Let's talk about that. Because that's another question I could ask you about a situation like this. Because why would you have written a negative in it? Because it's going down. The y is decreasing. Think of the chart. When y is decreasing, what's y prime? Negative, right? So, here's a question I could ask you. In this equation, is k positive or negative? In this equation, is k positive or negative? Sam? Okay? What's y? Positive or negative? Positive, right? Square root of positive? Positive, right? What's y prime? Y is decreasing, so what's Y prime? So this side's negative, right? This thing right here is positive. What's K got to be? Really? Okay, so if K is negative times this negative, isn't that positive? So if K is negative, won't this side be positive? Is that possible? Can this side be positive? Because what's Y prime? So I'll ask again, what's K in this problem? In this problem, K is positive, right? K is positive. Y prime is negative. This is positive because Y is the depth of the liquid, so it's got to be positive. So they knew, when they wrote this equation, they knew Y prime was negative, so they just stuck a negative here for emphasis, and then the K is going to have to be positive. But what if I was writing this, problem the way you and I talked about it last week? I said the rate that the liquid drops is proportional to the square root of the, I would have written it like this. Would that have been okay? Would this be okay? It'd be fine. But what will K be? K will now be negative in this equation. Does that make sense? They just stuck the negative on there for emphasis. But now, if this was the equation, K will now be negative. And if I ask you, is K positive or negative in this scenario, you would say negative, and then to tell Y, you'd say Y prime has to be negative because Y is decreasing, and Y is positive, so therefore square root of Y is positive. So the only way that this works, if this side is negative and this value here is positive, this has to be negative right here. Okay, but if there's a negative in the equation, so if there's a negative here already, then in that case, K's got to be positive, right? So you need to be able to look at a situation like this, be given that information, and be able to argue that as well. All right, anyway, they gave you this. So we've answered part A. So part B. So all of these different parts get into all the different things you should be able to do with a differential equation. Okay? Part B is a verify. Okay, so they say, well, we're going to claim that this is the solution, but we're supposed to verify that this is a solution, and it's divided by 4. Well, you know what? If I'm dividing by 4, I'm not dividing by 4. I'm going to write it 1/4. Okay, dividing just causes all kinds of headaches that are not worth it. So I'm going to stick that 1/4 in front. Okay, so did I do that right? I did not do that right. It's not square root, is it? It's squared. So it's C minus KT squared. So they're claiming that is the solution. So I'm going to do a T chart right here. And so I'm going to need Y prime. So I'm going to bring the 2 down in front. That's going to be 1/2. The inside always stays the same. This drops to a 1. And I got to kick out a what? Negative K. Because T is like my X. Anything multiplied times the X, we've got to kick out, which would be negative K. So this is going to be negative 1/2 K times a quantity C minus KT. Okay? And so that's my Y prime. So I'm going to put that over here, negative 1/2 K times C minus KT. And here I got negative K times the square root of 1/4 C minus KT squared. Right? Well, whenever I have a square root of a product, I can do the I can do the square root of each thing. If I have square root of A squared B squared, then that's just AB. I can do the square root of A squared, I can do the square root of B squared. Okay, so I do the square root of 1/4 is 1/2, and the square root of that is going to be C minus KT. And sure enough, if I just rearrange those a little bit. Okay, so part B is definitely something we have to be able to do, verify something's a solution. All right, so now that we've verified that that's a solution, we can move on to part C. Now it becomes an IVP. They've now given me some initial conditions. So, Y, I now know that Y is equal to 1/4 C minus KT squared, and they tell me that Y of 0 equals 9. Now what does that mean for this tank in this problem? What did they just tell me? So at the beginning, the tank has 9 feet of liquid in it. It's a big tank. Okay, it has 9 feet of liquid in it, right? So at the beginning, it has 9 feet of liquid in it. So I'm going to put a 9 right there. I'm going to put a 1/4 right there. I'm going to multiply by 4. I'm going to square root. Oh, now here's a problem. What about this? When I square root that, I get plus or minus 6.
It has to be positive.
Why? Here's the problem. Look what they said right here. For physical reasons, it's okay to assume that C minus KT is greater than or equal to 0. So C minus KT has got to be positive. For physical reasons. Okay, well, let's imagine what those physical reasons are. Let's come right back up to here. What did we just say about y prime here? Y prime has to be negative because y is decreasing. We said k is, what was k? K had to be positive, right? So y can be decreasing. So this is negative, this is positive, and we know we want this to be negative, so what's C minus KT got to be? Positive. This has to be positive times negative. Because we already know K has to be positive because of up here. So if K is positive, that means this has to be positive. So C minus KT has to be positive. Okay? So, because of that, only because of that, can we not put a negative 6 there. All right. So, and what I forgot to put in for 0 right there. Now, I wouldn't have carried this along that far. I would have just, if I was actually working, let me erase that and make that look better. I wouldn't have done all that. But it actually helped me. It actually helped me understand that I had C minus KT there. But I normally would have done 36 equals C squared. And then that actually would have made it tougher right there. Because I would have said, okay, C, why wouldn't I get plus or minus 6 here? But we got to understand that this side is really C minus KT. It's just that the KT wiped out with 0. Okay, so it isn't. So that actually made it harder to imagine. Okay, so C is going to be 6. So that now tells me that y is equal to 1/4 6 minus KT squared. Now they tell me another piece of information, right? 2 equations, 2 unknowns. They tell me that 20 minutes later the tank's down to what? 4. 20 minutes later, the tank's down to 4 feet. So this is going to help me tell how fast it is going. So I'm going to put a 4 in here. I'm going to put a 20 in here for T. I'm going to multiply that and get 16. 6 minus 20K squared. I'm going to square root that. I know that's got to be 4. Remember, this is my C minus KT right here. This is my C minus KT. It's got to be positive, so I don't need to do plus or minus there. So we take away 6, that's negative 2. So we get K equals 1/10 or 0.1. So I now know that y is equal to 1/4 6 minus 1/10 T squared. I now know the depth of my liquid at any time. So that part is solving a differential equation. They tell me the solution, but it's an IDP. They give me some initial conditions. So I got my y, my original y, but I don't know C or K, but they give me some values. I can just plug those in. I mean, that's not calculus. That's just algebra right there. I just plug in those numbers, and I find C, and I find K. All right, now I can go down to, we skip D. I go down to E. Oh, yeah, show that the tank takes 60 minutes to empty. Now, what would you do? 60 in for T. But I might ask you something else. I might have said, how full is a tank after 30 minutes? So what would you do? Put a 30 in for T. What if I said, when does a tank have 2 feet of liquid in it?
2 in for Y.
You'd put a 2 in for Y and then solve it for T, right? So there's a lot of different questions I could ask. And of course, the one they ask is, when is the level dropping at 0.1 feet per minute? Now, what's 0.1? Where am I going to plug in a 0.1? Not for Y. For Y prime. I got to plug a 0.1 in for Y prime. Well, now I got a couple of different Y primes I can plug into. I can plug into this one. I know what K is now. Or I could plug into this one over here. I got two Y primes. Which one would you rather plug into? 1 or 2? Okay? Doesn't matter really, but I would rather plug into 2. Okay, what did they want to know? What's the question saying, E? At what time is the water level dropping at point 1? So, if I plug in a point 1 here, I'll find Y. Is that time? That's not time. Now I know why you picked it. It's simple. Right? It's simple. But you could plug in, find Y, but then you'd have to go back to here, put that in for Y, and then you could find T. So that would work. But I would probably put my point 1 here, and then find my T there. Okay? Now, we already know what all these numbers are. So Y prime was -1/2. What was K? What's K? 1/10 times C minus, what's C? 6 minus KT, right? Isn't that what we have here? -1/2 times K, -1/2 times K times C minus KT. Wasn't that Y prime? Now, what are we going to do? We're going to put in place of Y prime a what? Actually, I've been leading you astray. I keep saying 0.1 because that's what you guys had said earlier, but it doesn't have to be -0.1. Haven't we been saying this whole time that Y prime is negative? Because Y is decreasing, it's dropping, right? So we got to put a -0.1. Okay? And then this is -1/20, 6 minus 1/10 T, and then solve it. Okay? If it's a no calculator problem, well, no problem. So we multiply that over there. Subtract 6, that'd be -4 equals -1/10 T. T equals 40. So it looks like at 40 minutes, right? I just multiplied -20 over to here. That gave me 2. Okay, I just multiplied that over. Could have distributed it, but I thought, why do that? That's just going to give me all kinds of fractions. So I just multiplied this over, subtracted 6. Okay, so at 40 minutes, it would be dropped. Okay, now I don't anticipate giving you one problem that's got all that in it, but every one of those, but all along there had different things we've done. T-chart, the C and the K got a little messy, so that was a little complicated, part of it. But just plugging in an IVP, an initial condition, plugging that in to get the C and the K. Okay, let's do, let's talk about 49 real quick. 49 is this whole idea of writing a differential equation. A small town charity fund drive wants to raise $65,000. According to Alfred E. Newman, you were talking about Newton's law of cooling. Anybody heard of Alfred E. Newman? You ever heard of Mad Magazine? That's the guy with the funny teeth. Look it up sometime. Anyway, it's kind of funny. Alfred E. Newman's law of cooling of enthusiasm. The rate at which people contribute to a drive is proportional to the difference between the current total and the announced target amount. Let Y be the current total T weeks after the start of the drive. 65,000 is the target amount. Does it sound reasonable? Is their enthusiasm proportional to the difference between the target amount and how much they've raised? So in other words, their enthusiasm would be high when what? When the difference is big, right? Like at the beginning. Does that sound reasonable? Okay, once you get close to, now you could argue once you get close to the goal, people get excited and they want to get it over the top, right? But at that point, what's happened? When they get close to the goal, what's happened? Most people have contributed that are going to contribute, probably, right? And so all of a sudden, you're trying to get those extra contributions. Now, again, like you say, you could argue that as you get really close, people get excited and might contribute. But at the beginning is when you're going to get the most contributions, probably, is kind of what they're saying. Okay, I think it sounds reasonable. Express this as a differential equation. Okay, so the rate of giving, or the rate that Y changes, Y is the amount they've raised. So Y prime would be the amount, or the rate that they're raising it. So that would be the measure of your amount of enthusiasm, the rate that they're raising money, is proportional to the difference between their target amount and the amount they've raised. It's just like Newton's law of cooling. The rate that the coffee cools is proportional to the difference between the room temperature, right? Now, let's talk about this. Is K positive or negative? Well, let's start with Y. Is Y positive or negative? Is Y positive or negative? It's the amount we've raised. It's positive, right? It's the amount we raised. Y is positive. Is 65,000 minus Y positive or negative? Positive. It's 65,000 how much we want to raise, so Y's got to be small. Okay? So this is positive. Okay? What's Y prime? Y prime's got to be positive because Y is, hopefully, Y is increasing. See how you're using chart stuff here? Y is increasing, so Y prime better be positive. So this side's positive, and this is positive, so what's K got to be? Positive. Now, what if it just said the difference between? What if I would have written it this way? Okay? Now, is K positive or negative? Well, Y, of course, is positive. But what's Y minus 65,000? The parentheses are now negative. Now, what did we say Y prime is? Since Y is increasing, Y has to be positive. So in this scenario, what's K? K's got to be negative, right? See what I mean? So that's how you would reason that out if I asked you that. Okay? Again, you're using the chart. You're using the chart as your explanation. Okay? All right, let's talk about 10. 10 said IDP. Some of you were coming in and asking about 11 and 10. 11, I don't think. Did 11 have an initial condition on it? No. See, that's the difference. 10 is just a differential, or 11 is just a differential equation. They say find the solution. A 10 is an IDP, but it's the same thing. It just means we do one extra thing at the end. So let's do 11 first. So solve this means find the original function y. So let's just practice on our derivative and antiderivative rules. What's the antiderivative of 2e to the x? 2e to the x. What's the antiderivative of 2 to the x? Now remember, the derivative of 2 to the x is this, right? That's the derivative of 2 to the x. But we're doing the antiderivative. So we're probably going to have to tack on that. Remember, we did one of those earlier? Remember, 1 over ln2 is just a number. It's just going to hang out there. Let's check it with the derivative. So this 1 over ln2 is just going to hang out there. And we do the derivative of 2 to the x, we get that. Oh yeah, we'll have 2 to the x, ln2. We'll have a 1 over ln2 hanging out there. They'll cancel, and I'll get my 2 to the x. Okay? Plus, what's the derivative, antiderivative of 2? 2x. Plus some c. If you leave off the c, I'm not going to count it wrong today or tomorrow. Okay? But there'd be some c, and we'd be done. The only difference when you add in an initial value is just like we got done doing with Torricelli's law. We can now plug those numbers in to figure out what the c is, like we found the c and the k in the other problem. So, the only difference, so we do exactly the same thing. So, antiderivative of that's just 3e to the x. Again, this is a very similar problem, so 3 to the x and 1 over ln3. Now, that's not really a rule. We're just doing that. We need to put on that 1 over ln3 because we know when we do the derivative, we're going to tack on an ln3. So there better be something sitting there to cancel. Just like with sine 2x, we know we're going to kick out a 2. So if we're doing the antiderivative, there better be a 1/2 sitting there, right? So when that 2 kicks out, it'll have something to cancel it with. And then the derivative or antiderivative of 1 plus c, right? And so now though, so instead of stopping like we did here, we now can plug a 0 in for x and a 0 in for y. So we can put a 0 here, 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 and now we can figure out what c is. So what's 3e to the 0? 3. 3 to the 0 is 1 times that is just that, plus 0 plus c. So what do we do to get c? We just move those over. So we'd have a 1 over ln3 that'd be positive, and then minus, so C would be that, but we're not done. I shouldn't even have circled it. This is a problem people run into. It feels like you're done. You just solved for C, so it feels like you're done, but what do you need to do with it? You need to put that right back then. So your final answer actually is the red thing. Your final answer is 3e to the x minus 3 to the x times 1 over ln 3. If that bothers you and you want to put 3 to the x over ln 3, I'm fine with that. Plus x plus 1 over ln 3 minus 3. That's actually your final answer. Okay? So the only difference is we do our antiderivative, right? Stick on our plus c, but oh, they gave us an initial condition. So let's throw that in there. Let's figure out what c is. And then that is our original equation. Okay, so only difference, IVP tacks on an initial condition. Here's just a regular differential equation. Okay, like so. All right. 14 was a verified problem. You know, again, normally might not go through all of it, but I mean, we got a quiz tomorrow, so you know, might as well better look at it here. So again, it's an IVP. They've given you the original and an initial condition. So how does that work in a verified? Well, sometimes, okay, sometimes the solution works right up until the point of the plus C part. The initial condition doesn't work. So the only thing different in a verified is we do our T-chart like normal, and then we have to plug this in. Matter of fact, I could do it right now. Well, I did it right down here. I said, well, I better make sure this works. So I put a 0 in for the T, and I get e to the 0 is 1, so I get 100 plus 50. Oh, okay, 150. So I was just double checking that when I put a 0 in, I get out 150. I got to make sure my initial condition works. Okay, so you should show that on your paper. So I'm not only going to verify the T-chart part of it, but I have to verify the initial condition works too. That's all it adds to it. Okay, so I'm doing my y prime here. The 100 will go away. I'm going to kick out a 2. E to the 2t. The derivative is e to the 2t, but kick out a 2. So that makes that into 100. E to the 2t over here. This would be y is this. Right, here's y right here. Minus 100. The hundreds will cancel. So I got 2 times 50 e to the 2t. Oh, yeah. Check. Okay, so that's just your verified. It's just your verified, but added on, it adds on that one extra little part. Okay. All right. Okay, on 55, they go through the whole story. Again, it's very much like Torricello's law. They explain this whole thing. They give you the differential equation. They first give it to you in words, but then they go ahead and give you the differential equation. And then they give you what they say is the solution. So the first part is just show or verify. Okay, so P prime, let me quickly do this. That goes away. The 0.1 is going to kick out. We're going to have e to the 0.1t times a 0.1. Okay, so that's my P prime. So it would be 0.1c e to the 0.1t. This would be 0.1 times P. That's 1,000 plus c e to the 0.1t minus 100. So if I distribute this, this would be 100 plus 0.1c e to the 0.1t minus 100. Sure enough, the hundreds cancel. Okay, and it checks. Right? So I do my P prime over here, put it in for that, put the P in for that, everything checks. Okay, so now I can use this. Okay, so then it says, if I put $2,000 in now, how much is it worth in 10 years? Well, if I put $2,000 in now, and this is where you got to be careful. Does $2,000 go in for the C? Remember we were talking about this? You guys were wanting to put that in for that initial condition. Is $2,000 go in for the C? No. $2,000 is the amount you put in at time 0. So you put in a 0 for now, and you have 2,000 is your principal. So we subtract the 2,000. E to the 0 is 1. So we get C is 1,000. So the equation is P equals 1,000 plus 1,000 e to the 0.1 t. So that is now your solution. Okay, so it's like an initial condition. What they gave you P of 0 equals 2,000. Right? They gave you an initial condition. So I put a 0 in for the t, and I put a 2,000 in for the principal. So now I have that, and then the question is, how much is it worth in 10 years? So I'm going to stick a 10 right there, and this will be a calculator, right? Stick a 10 right there, and see what I do. Okay? Again, same stuff we've been doing. Verify, be able to plug in, find values. Okay. All right, if go back to all of this. Okay? What we haven't done hardly anything of right now is this. But that's the older stuff, so I think we should be better at that. This is the newer stuff, so I wanted to make sure and spend plenty of time on that. Okay, so we've done a lot of work with that here today and on Friday. And then, of course, we've gotten into our derivative and antiderivative rules a little bit as well. Okay, so now let's finish it up with that. So, 41. Now, some of you didn't notice, you got to look pretty carefully. But on number 41, that x is not under the square root. If that x is under the square root, it's a whole mess of a problem. It's there's no way it's no calculus. Okay? So this is the function right here. And on 41, you're supposed to do local max, local min. You're supposed to do all that stuff, right? Inflection point, do your number lines, okay, all that stuff. So I went ahead and did g prime, set it equal to 0, added the square root of 3, divided by 2. When does cosine equal square root of 3 over 2? Cosine is the x, remember. Pi 6 and 11 pi 6. Right? Pi 6 and 11 pi 6. Okay? And if you get those wrong, it doesn't mean you can't get some points down the road here. If you get those wrong, you do a chart, you take your wrong answers here, and you do a correct chart. You know, obviously your answers are going to be wrong at the end of the day for your intervals, where your local max and mins are and everything. But there are some points to be had for doing that part of it correct, even with your wrong numbers that you have. Okay. All right, so I'm going to do a number line. Right, I'm going to pick some numbers in here that would be good. I think our interval on this one is supposed to be 0 to 2 pi, isn't it? Okay. I'm going to plug back into here. Remember, this is 0.86. No, square root of 3 is like 1.7. Okay. It's between 1 and 2, obviously. It's between square root of 1 and square root of 4, closer to square root of 4. So if you don't have that memorized, you can get a pretty decent idea. Put a 0 near cosine of 0 is 1, so 2 minus that's a positive. Cosine of pi is over here is negative 1, so negative minus that is going to be negative for sure. Cosine of 2 pi is 1, so again, same thing. I'm not going to go through all of those justifications. We've done it a bunch of times. There's a local max, there's a local min. Here's where it's increasing, decreasing, increasing. Okay. Global max min. Global max min, we would do a list of candidates right now. Don't say F if the function's G. We do G of 0, G of 2 pi, those are our endpoints. Do G of pi 6. Do G of 11 pi 6. Okay? Now, if this is a no calculator, it could get a little messy here in figuring out what's what. Now, I don't want to take a ton of time to do this, but just arithmetic. But when you put your 0 back into your original, sine 0, 0, so that's easy. 0, that's easy, so that was an easy one. 2 pi, not as easy. Sine of 2 pi is 0, so that becomes 0. But now you get square root of 3 times 2 pi. So you get 1.7 times 2 pi. Well, that's about 3.4 pi. That'd be like 3.4 times 3. It's 9, 10 something, roughly. Real rough, but hopefully I won't have to get that accurate. It's about 10-ish, right? Yes.
Wouldn't that be negative?
Maybe.
Minus.
Yes, it's 0 minus. Thank you. Yes, very good. Okay, now let's put in pi 6. Now to really get interesting because we're going to get some fractions. So sine of pi 6 is 1/2 times 2. So that's 1 minus, I'll put it here, 1 minus, and then I'm going to get square root of 3 times, now what's pi 6 roughly? What's pi 6 roughly? 3 over 6, right? Pi is about 3, 3 over 6, it's about 1/2. So this is 0.5. Okay, so square root of 3, 1.7 times 0.5, about 0.8, 1 minus 0.8, roughly. So this is about 0.2. Okay, so we got about negative 10 something, we got 0. Okay, 11 pi 6, well that's almost 2 pi 6, right? I mean 11 pi, that's like 33 over 6, it's like 5 point something, 5.5-ish. But I put 11 pi 6 in here, sine of 11 pi 6, that's negative 1/2, 2 times negative 1/2 would be negative 1 minus square root of 3 times, and what I say that was, 11 pi 6 is roughly 5.5. Okay, well this is going to be a big negative. I mean, think about this. Square root of 3, that's almost 2, that's going to be like 10, 11. Right, something like that, almost negative 1, but it is pretty close to this, and so that, I wouldn't give you one like that, I would give you one that was pretty obvious. I'm not going to give you one quite this messy, okay, so use your calculator to finish that one out, that's fine, but it's probably pretty close to this one. Well, think about it, 11 pi 6 is pretty close to 2 pi. 11 pi 6 is pretty close to 2 pi, so you plug in 11 pi 6, but actually we could think about it, because what's happening after 11 pi 6? What's G doing? Going up. After 11 pi 6, G is going up. So which one of these has to be bigger? Which one has to be bigger if the graph's going up after 11 pi 6? This one, right? This one's got to be a bigger y value than this one, because after 11 pi 6, this graph's going up. So this must be the bottom, right? So this must be like a negative 11-ish or whatever, okay? Pretty close, though, to this one. But again, look at the number. After 11 pi 6, the G graph is increasing. So it's got to be going up. So this has got to be bigger than 11 pi 6. So our max looks like it's here. And again, what's happening? 0 and pi 6 are pretty close. But what's happening? The graph's going up. So which one's got to be bigger? Pi 6, got to be there. So what's happening is this graph's going up just a little bit, and then it's going down a bunch, and then it's going up just a little bit. That's what's happening. So your global max has to be there, and your global min has to be there. So your max has to be at pi 6, and your min has to be at pi 6. Because the number line's telling the story. Okay? All right, and then you would repeat that for inflection points. You would do double prime, set it equals 0. I'm not going to go through that. It'll give you a little bit of work done. But that also gets you into the global max min stuff. Okay? All right, one last time here. Let's go to our calculators. Everybody get your calculator out because we've done a lot of no calculator stuff. The main thing that you'll use your calculator for, the calculator part will be for in this quiz, is probably going to be like your bank interest kind of stuff, or like Torricelli's law, if we need to plug in like e raised to something. So if we're doing something with an exponential or something like that, and we need to plug values in, the calculator will be a good thing to use, okay? The other thing, the other main thing we're going to want our calculator for is going to be a chart, global max min problem, where it's some function we can't easily do, okay? So here was 45. So, derivative, here it's going to be negative 1/2 sine 2x, but then we're going to kick out a 2, so that's going to cancel that, and we're going to let that equal 0. But we could, and I should have had a presenter, but too late now. So we could let the calculator do that derivative for us. But now, again, it's better to be practicing your derivatives and make sure you know how to do that. Okay, so it's going to be negative sine x minus sine 2x, right, equals 0. So that's our f prime. So I just want to make sure everybody understands that now to solve, so menu, algebra, solve, what was it again? Help me out. Negative sine x minus sine 2, did I do it right? Let's don't, is that what you guys agree with that? Am I good so far? And then what do I put? Equals 0, comma x. Then I go outside of the solve and do what? Vertical bar. Because if I didn't, and I just hit enter right now, I would get that, right? So if you forget, you're going to see these N1s and all this mess, and then that should trigger, and you should go, oh, oops, I forgot to limit. Now, if you get that, and you come up to me on the quiz and ask me what to do, I'm just going to, I might say at the most, I'll probably say it for the quiz, don't forget about the vertical bar when you solve, okay? At the most, I'll say, well, you got to put a vertical bar. Okay, that's the most I would say, okay? And then you would go, what's this one? Negative 5 to 5? 0 to 5. So 0 less than or equal to x less than or equal to 5. Okay. Hit enter. Probably hit control enter. But if I didn't, if I just would have hit enter, oh yeah, that's actually better. I probably would just hit enter and get that. Well, although if you're using your calculator, decimals aren't bad. The only problem is you could get into rounding errors, so this is fine. So 0, 2 pi thirds, 4 pi thirds, but it might just give you decimals anyway, right? And then pi's in there too. So I actually got 4 of them. Okay, so x equals, what was it, 0, 2 pi thirds, pi, and 4 pi thirds. So that's a number line with a lot of stuff on it. Okay, now 0's at my far edge. So to be honest, now, whether you want to put something on the left of 0, since that's not in our interval, that's okay. Sometimes we say local max mins we're not going to count them at the endpoints as local max or min. So if they're at the endpoint, maybe we won't count it. But if you do, I'm not going to count that wrong. Okay. A lot of times we say, hey, since it says, right, and 4 pi thirds, is that still in our interval? Well, it should be because we did the solve. Yeah, that would be. That'd be inside our interval. Okay. So now it's a little harder to find some numbers here, but we can. Pi thirds. What's between 2 pi thirds and pi? 5 pi 6 would be, right? 7 pi 6 would be in between there. But you could probably come up with some decimals too, like just 3.2. 3.2 would be bigger than pi. 3 would be littler than pi. But you know, so it's not like you have to use these kind of numbers. You could just use some other decimals that you're sure would be in there. We could use 5. You could go over here to -1, but you got to be careful here because there might be another one. So you got to be kind of careful. You better put a number that's just barely to the left of 0 because you don't know. There could be another 0 over here somewhere, right? And we might not. We probably shouldn't put -1 there because we really don't know what's over there. So better that's why it's probably best to just leave that alone and not put anything to the left of 0. To be honest, that'd be I'd rather you do that. Okay. All right. Then we plug those in, and has anybody done this already? What do you got? Probably have. What do I get in here after the 0? Remember, we're plugging it back into here. You agree? Anybody agree? Positive, negative, answers in the back, so you can get that. Positive, so again, there's local maxes, local mins, the whole thing. It's asking for local max and min, and it's asking for inflection points. So then we would do the second derivative, set it equal to 0, again, using our calculator. So the only difference is we get to use our calculator to help us solve it, but we still do our number line, we still give all our same rationales, our justifications, all that. Okay, if they ask global max min, you would plug those back into the original, take your endpoints, 0 and 5. You would take your stationary points, you plug those back in. Okay, but you just got to be able to use your calculator. So I just want to make, and remember, when you plug those back in, that's when you can type in your original, do the vertical bar to type them in, but you don't use solve. Okay, it's only when you set it equal to 0 that you're doing the solve. Okay.
So that means like if we're not doing the like the sign graph like before 0, that means we can't put the 0 for local max.
Right. So if you don't plug anything into the left of 0, which I think is a safer bet, then you're not going to give the zeros a local max min, even though it may be. Okay. But typically what we're saying is we're going to have a local max or min. We got to be able to see on both sides to see what it's doing. And if it's at our endpoint, we don't care about what's on the other side. So that's why we usually don't include that as one of our local max mins. And so I won't cap on that. All right, that's it. That's it. We went through the homework pretty steadily Friday. I know we've done a lot. And so if you had nailed this homework already, felt really good about it, well, you're ready to roll. Okay, you're ready to roll. Because that's pretty much the things that will be on the quiz. The only thing we didn't spend much time doing here, we did within the problems, was just the whole idea of derivative, antiderivative. Why don't I throw one problem up here just for quick practice. This would be as hard as it would get right here. Well, I don't know how hard as it would get, but okay. Find f prime for me. Find big F. Oh, on the big F, we can't do big F of a log. There is no rule for big F of log. So forget the log when you do big F. Just do big F of the first two terms. Okay. I would never ask you that on a quiz. So I kind of forgot that when I put it on there. So just do big F of the first two terms. All right, has everybody got little f written down? Everybody's got little f written down? Okay. So I'll put up those answers here in a minute, but if you feel like you've got it, let me put up the homework here, and then I'll put up the answers here in a minute. Now, I'm not going to check this. This is review. This is another assignment very similar to the last two we've done. But again, it's pretty, 2.5, those difference equations, 8 and 9 are like 10 and 11 were today, with the IVP and the, and solving or whatever. 26, 27, 44, 45, so those just get into verify, just kind of the whole verify thing. Verify something's a solution, do an antiderivative, plug in, find the C value. Here's again a few more of those with e to the x and kind of that kind of thing. So that's just that differential equations using kind of your antiderivative rules a little bit. Okay, and then your chart stuff. Again, a calculator 146. It's just like 45 that we just did. And then I just threw one up here. This is kind of like number 41. Kind of like I said. Why did I say 21? Like number 21. I didn't mean number 21, I meant number 41. It's like number 41 that we just did with the no calculator. Okay, so there's some chart and global max min. And then the review section, the chapter summary section, which in the answer book they call 2.8. Here's just some problems that kind of review what I just put up, derivative, antiderivative rules, some more stuff. So that's just some stuff. I'm not going to check it. That's just some extra practice for the quiz.
Is 2.5 to 2.7 required then? Or is it just the review that's optional?
Oh, it's all optional.
Oh, the entire thing. Okay.
The entire thing. I'm not checking any of it tomorrow. Right? This is for you to get ready for the quiz. Okay? I think it's pretty similar to what was on the assignment sheet. But I've added a few things. There's a few things additional to what's on the assignment sheet there. So.